science colloquia that this department, statistics department, ISER data science and Plain University, we have sort of come together and we have started this last year. So this is the next one in this series. Vinay is a TCS fellow at TCS, and there was some discussion about TRDDC here, which you heard live. He heads the software and systems research group. He's really a TRDDC veteran. IIT Madras, Madras had not become Chennai back then. IIT Madras alumnus. He's fellow of the National Academy of Engineering, a visiting professor at Aston University, Middlesex University, and IIT Jodhpur. So, without further ado, I would request him to. Thank you.
So what I'm going to share with you is the work which we started about roughly 10 years ago. Uh, and it's about trying to address complex decision-making problems, initially in enterprise space. We also realized that this technology has application to other spaces also, like societal spaces, cyber physical spaces, etc. So what I'm going to share with you is why we started this and what sort of impact it has had. You people know simulation far better than me, so I'm not going to go into the details of simulation at all. I'm essentially a programming language guy, and model also you can view model as a program in a slightly different language. It is a modeling language. So what I'm going to share with you is uh, how a typical software engineer would look at the simulation, modeling and simulation world in order to use simulation as a tool. Otherwise, for us, compiler is only the tool. The simulation is another tool which we have to use. How do we go about it? That's the idea. And I will try to focus, therefore, I will try to focus on the problems and what kind of software-ish architectures or software-ish take is necessary in order to solve that problem. And I will try to present a justification of why we have done what we have done. For you, it will be nice if you agree, but if you don't agree, that's not a fact. So, to give you a backdrop, I work for a commercial company, and even though we are TRDDC research, we still have to make ourselves useful in some way or the other. Not every time, but at least once every 5 years or so. So it was relevant to focus on what TCS is all about, and we should do something what is of use to TCS. So, in generally, not generally, always TCS has been in the business of offering software solutions or services to large enterprises. So typically, enterprises can be viewed along these three planes. The topmost plane is the strategy plane, wherein CXX management defines goals and the strategies that should suffice to achieve those goals. This strategy plane is supported by a processes plane, which is all about operationalizing these strategies, not necessarily automatically, but operationalizing these strategies. So you will define roles, responsibilities, workflows, and stuff like that. And the bottommost plane is that of software systems, who these software systems come into existence with the sole purpose of providing mechanical advantage through automation. So they try to automate these business processes as much as possible. That's the name of the game. TCS in those days was focusing solely on the software systems plane. We were known as software solution providers, and therefore, most of our work in those days, as late as 2010, was focused on how to develop software faster, better, and cheaper. And much of the work which we did led to products which TCS used, and hopefully it must have helped them. Uh, Apologies for singing our own praises. But this was the time when we realized that if you stay restricted to the world of programming languages, wherein a program is nothing but a stream of characters. It doesn't have any better structure to it. There isn't really much which you can leverage when it comes to construction of a program. But if you are able to capture the structure to which that program conforms to right at the beginning and provide behavior of what that program is supposed to do in a more intuitive, closer to the problem domain manner, then from this specification, it becomes a lot easier to generate an implementation of a program. So basically, you treat a programming language and all other paraphernalia like a typical database or a typical graphical user interface or a middleware which connects the graphical user interface, the server, and the database together. You treat these things as primitives. You have your specification, and essentially you write a compiler, which is just going to compile your specifications into the primitives offered by this four technology. That was the idea. I mean, not a great idea, because compiler was the only thing which we knew. So that's why we did it like that. But this, the world thought, ki, oh, this is a very nice idea. And it just got, as Mihir was saying, they are very good at coming up with acronyms. So we came up with an acronym called model driven code generation. Then later said, I mean, why limit ourselves to code generation? So then the new acronym which is famous is model driven engineering. Okay, so we were one of the first to do model driven engineering. That's the cutting the long story short. And this work probably did help change the image of Indian IT industry. Again, apologies for singing our own praises. It came on the first page of New York Times and International Herald Review, saying that in India it is not software police. They are doing something which is really cut off the cutting edge of the technology. I mean, our CEO was very happy with it. I mean, that's always a good thing, isn't it? So then, in 2010, etc., we started realizing that there are three parameters which are going to hit us. First of all, if you start, there was a monitoring aspect. If you are just delivering a software, your revenue per employee is low. If you are delivering software which helps strategy guys do their job, you can't say you do their job, right? Help them do their job better, then you suddenly can charge lot many, whatever they call it, so many dollars per hour, etc. So that is much, much higher. So not a linear, almost a geometric progression. Uh, and But in order to do that, you also need to have a really deep expertise and experience. Otherwise, you can't play in the strategy field at all. But thanks to advances in AI, initially NLP, later on generative AI, it's became very clear that the lower strata of this picture, uh, you are that much more vulnerable to be replaced by a machine. So effectively, TCS today has 625,000 people, largely people addressing lower strata. So there is a worry that, I mean, that work just might not exist. Not now, maybe 10 years from now, maybe 5 years from now. So we felt that maybe we should do something different. And that something different then was, can we start addressing problems which are there in the strategy plane? And over there, it also became clear that earlier enterprises used to be an island having these three layers. Soon, enterprises started becoming complex ecosystems wherein these kinds of islands are talking to each other in a dynamic, not necessarily predefined manner. Therefore, trying to do a good job of arriving at the right strategy, etc., became that much more difficult. Or rather, the strategy gurus were willing to admit that they will need some technological help to solve their kind of problem. So we had a kind of a toehold into that space. And we felt that let us try to solve a problem which is generic enough so that if we end up solving that problem reasonably well, we should be in a position to instantiate that template across many different verticals. So we never felt that we are solving a problem for a bank or for something. It was generally for enterprise. Any enterprise should have that kind of a problem. And therefore, if you have a solution, they will like to have a solution. And I will share with you some examples uh, intentionally from different fields so that you will be able to judge for yourself how far we have been successful. Now, let us try to see how this decision making problem is addressed. Typically, decision making problem, etc., these system dynamics people are the guys who generally look at that, solve that problem. And their point of view is what this picture is trying to tell you. So,
People might not know about system diagram.
okay, I'll come to this. Right. No problem. Yeah, so here is a point of view. Forget about the system dynamics. Think of it as systems engineer. People look at it like this. So they say that the system, which is that blue box and some complex contraption inside it, that blue box is the system which exists because it certain goals are there, those goals need to be satisfied. That system is operating in an environment which is intrinsically dynamic, and you don't necessarily have all the information about the environment with you. The system takes some input and gives you some output. Goals can be viewed as some sort of an objective function onto the output. And so now the problem then is for the given set of input, uh, check if I'm getting the right set of output. One should observe the changes that could be taking place in the environment, changes in the goals, if at all, and then see if this output is still a reasonably decent output, so that the goals can be met. So there is a lot of sensing and sense making that happens, which currently is done by human experts. And if not, these human experts are expected to introduce the right kind of interventions. And yeah, it's kind of a so you the idea is to nudge the system till it finds itself into the right band of output. That's the problem. And there are three techniques, broadly three kinds of techniques which are used. First is based on mathematical rigor. If this blue box over there is amenable to purely mathematical expression, let's say partial or ordinary differential equations, then you could solve this particular problem maybe as a linear programming, any other problem. So you have a precise description of what the system is, and there is a mathematics underlying that system. You express it and solve it. The unfortunate part is enterprises like a bank or PCS itself is an enterprise that is just not amenable to pure mathematical expression. Much of the uh, business and societal or socio-economic systems are not amenable to pure mathematical expression. So that's one problem. Uh, uh, so therefore, pure mathematics doesn't really help. But there will be parts in a complex system which would be amenable to pure mathematics, which of course you can use to solve that. That's not a problem. Second thing is techniques which are based solely on data. So it's like, okay, this system is too complex. I really don't understand I'm not going to worry about understanding the system so as to be able to specify it in one way or the other. and the new system has worked till date. Now, can I now conceive based upon the past data of the system and use that particular model for future predictions, which sounds the right way to go about, especially when now that we have fairly sophisticated machine learning algorithms, etc., ready. But this is akin to you have a fun car, big windshield, but you have chosen to drive looking at the rear view mirror. Because all that you are saying is things in the future are going to be what has happened till now, which is not such a bad assumption. If uh, the system is linear, but if system has a lot of non-linearities, etc., then that assumption kind of doesn't hold, and no one knows whether the future is actually extrapolatable from the past. So relying solely on past data to decide what the system behavior, what to arrive at a model of the system is fraught with danger. But there are again spaces where these techniques work, but not always. And therefore, finally, the last recourse is human experts. When both these techniques fail, you go to a guru and say, "Ki, boss, this is the problem, how to solve it." Almost always gurus are able to solve the problem. The trouble is they are never able to explain why they chose one particular candidate amongst the other candidates. That they are not able to explain. Because modern enterprises are complex systems. So they spread across a very wide canvas uh, and multiple domains of expertise, which means that you need, if there are n domains of expertise, you need n gurus to solve that. If you want to take the human expert-centric approach, and that also is fine. You might be able to get n gurus, but the trouble is, a guru only knows about her domain. So she might be able to say what is the best solution for that particular domain. But the ripple effect of introducing that intervention, which seems best as per that domain, onto the rest of the system, uh, guru doesn't know, and if guru doesn't know, no one knows. That's the problem. So therefore, generally these systems tend to lurch from one unstable state to another unstable state, wherein eventually people say, "Ki, okay, boss, let's leave it." So that's the current state of the practice. Now, what we thought was, would it not be nice if we had a machinery which could help us perform this? Okay. So what you see over there is a goal decomposition architecture. So it's I want to achieve this goal, which means these two goals should be achieved, which means these two goals should be. So you kind of do a goal decomposition along with interference of goals. So certain goals may interfere positively, interfere positively, which means that if you solve a particular goal, solving the other goal becomes that much more easier. Or some goals may interfere negatively. That is, if you achieve a particular goal, then you may have to just let go of that other goal. There are trade-offs basically. And goal is nothing but an objective function on measures. So measures are the things which you can measure, obviously. And levers are the capabilities. Levers influence the measure. Okay. Now, would it not be nice if we had a machinery which will help me tweak these levers? That's your control variables till your objective function holds, which means the goal is met, and this will basically go bottom up. So you keep on tweaking your levers, see what is the effect onto the measure, and boom, this kind of measures are fine. So it means these lower level goals are met. Then a goal which is met is now just like a measure. It's just a value now. So this now becomes measure, and then you try to do the similar tweaking till you get the goals, etc. So like that, the intuition was if we could provide a machinery through which this kind of a bottom up uh, satisfaction of goals with a human in control technique would be what the decision maker could benefit from. Mm. Now, when we try to look, what do these decision makers actually do? So, first is they uh, analyze. So think of system as a transfer function from input space to output space. It has a certain set of measures, certain set of levers. Then your goal is nothing but an objective function over your output space. Then there are certain set of perturbations which you know the system is likely to face. Then the analysis task is you just check if the goal is met and will the goal continue to be met even in the presence of certain perturbations? That's the analysis use case. Second use case is control, wherein you start with the condition that goal is not met, and there are certain set of perturbations which the system is likely to face. Now you need to identify what should be the changes in the levers so that the goal is met. Again, that tweak the levers, look at the major, that kind of problem. The third use case is explore, wherein you say that, okay, I have this system, and this system has these n constraints, of which k less than n are non-negotiable constraints, but the other n minus k are constraints that can be relaxed. So if I am willing to relax those constraints, is there a better state possible? And how much better that state is? That's the exploration use case. And the final use case is transformation. So through exploration, you have found a better use case. You know what is your current state. Can you now provide a path from the current state to the desired to be state with a priori assurances that you will eventually reach over there? So decision making has these four shades to it, and the technology that we develop tries to address both these three shades. And now you start with some knowledge. In the process, your knowledge may become better. And the fact that now you know more about a particular domain means you now have better capabilities. So your levers L now become L prime. Other capabilities, maybe the transfer function from input to output that is now different or better. And your measures are also now better. You may have more visibility into the space. So now you are able to do more observations. But once you have those L prime, the new transfer function and L prime, the rest is still the same. That's the idea. So what we came up with is a simulation based approach to support these tweak the levers, observe the measures, and check if the goals are met or not. So this approach essentially is founded on three pillars. One first is the pillar of modeling and simulation, from which we borrow the idea of a digital twin. Now, over here, I would like to say that our digital twin is better than a model that is learnable from the past data. Uh, that obviously is a part of the digital twin, but the digital twin also allows you to specify art of the possible, which a model which you can learn from the past data lacks completely. So digital twin has both things put together. Second pillar is that of artificial intelligence, from which we borrow the ideas of machine learning and reinforcement learning. I will quickly come to how we use the reinforcement learning. And third pillar is that of control theory, from which we borrow the idea of uh, model reference adaptive control paradigm of talent control. Now let's step back and look at what do we mean by enterprise digital twin. On the left, you have a classical definition of digital twin. It is a digital twin of a physical system. Now, that physical system is governed by the laws of physics, and therefore it is very well understood, and you know its behavior can be encoded in suitable mathematics. So here, digital twin is unable to purely analytical expression because you know everything. By enterprise digital twin on the right hand side differs from digital twin of a physical system in the following ways. First of all, its behavior is not governed by any laws per se. Second, we don't have complete information about the system which you are trying to deal with. Uh, and therefore, because you don't have complete information, there is uncertainty, and that uncertainty needs to be expressed in the specification of digital twin. So the specification of a digital twin, by definition, is stochastic. It is not fully deterministic. And digital twins and the spaces where spaces like society, enterprises, businesses, they have this fractal nature. I mean, what seems like a big thing, if you open, you see there are many chota things which are connected with each other. If you open that chota thing, there are still more chota things connected with each other. So, uh, the digital twin, therefore, must be amenable to composition so that when you compose things together, it is also a digital twin. That's that's generally not the case with the digital twins on the left hand side. So as I said, we are essentially programming languages people. So if you have that kind of a digital twin, then you need some model of computation and you need some language to specify that digital twin. So we borrow heavily on the actor model of computation, which was introduced in 1979 by Gulaga as a part of his PhD thesis at CNU. What is actor model of computation is a perfectly asynchronous model of computation, where each actor is autonomous. It reacts to the things that are taking place in its environment, and it acts in a way that it helps achieve its goals. It also makes use of other actors so as to achieve its goals. That's the model of computation, and it is perfect asynchronous. So an actor sends a message, but it doesn't necessarily wait to get that message processed and then carry on from there. Perfectly asynchronous. So what you see on the right hand side is broadly the language. So actor has a state, which is a set of attributes, pretty much like your C++ class. It has a behavior, again, pretty much like your C++ methods, C++, Java, whatever programming language you are comfortable with, but it's a event-driven paradigm. So the behavior is on occurrence of a certain event, and if a particular condition holds, then perform some action. Now, this will be a purely deterministic behavior. Since it is stochastic, you have a probability distribution over these actions. So you say that action one at probability P1, ting, 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 up to action in probability P. That's it. Now, this is what you, this probabilistic probability distribution depicts how much you know about that actor. Over a period of time, this probability distribution may change. And that's why your actors in a way needs to be self-adaptive, self-learning. But that is something which we have just now started working. So let me not make complete fool of myself by talking about it. So an action can either change the state, means it will change the values of its attributes, or it can send a message to another actor to do something, or it can create a new actor, or it can become another actor. Become is like in object-oriented paradigm, you just cast yourself to become some other object in the object hierarchy. That's the closest approximation. And message is nothing but event and the relevant data so that whomsoever is receiving that event will then be able to process that event. Okay. So the beauty is in this actor model of computation, you don't really need to know the entire system behavior at all. You just need to know the behavior of the various actors that comprise the system. And as these actors go about doing their job, the overall behavior of the system emerges. So you don't know it, but it emerges. That's the essential difference. So the technological infrastructure to support this model of computation is as follows. So now we want to support these four use cases: analyze, control, transform, and explore. So far, we have only supported analyze and control in real world. Transform and explore have been supported in laboratory, so I will not talk about it. Now, think of it. We said that this specification has these four colors. A, uh, because the information that we have can be put into these four dabbas. Okay? So you have these known knowns, meaning I know everything about the system and I know it with complete certainty. Then there are these known unknowns, which means I know everything that needs to be known about the system, but I'm not so sure about my knowledge. So over here, oh God. So over here, you have the knowledge, but you don't necessarily are 100% certain about that knowledge. But it is still amenable to specification as a programming language. So over here, uh, we these two boxes can be specified either using an actor language, as I said just now, or it could be specified in terms of system dynamics or stock and flow models, as they call it. Implementation that we support is Java with actor model extension. Java is an extensible programming language, so we have extended Java to be so, and it's not proprietary, just available for anyone. Validation, unfortunately, we are not very strong. Uh, right now, we say ki you construct your digital twin, test it, and see if it is working correctly or not. If not, you go back to the drawing board and change. So basically, we are treating it just like a program. We are not using any formal methods or some clever stuff to check whether the specifications themselves are correct or not. Can be done, we are not doing it. And the second thing is when you don't have the knowledge. So knowledge is not available with you, but you have the data available. I don't know enough about the system, but I know how the system has behaved. Now uh, uh, you can train a deep neural net with the available data. The fourth thing is unknown unknowns, means it is actually unknowable in some sense. Or I don't even know what I need to know. That kind of situation. So over there, obviously, you don't even have data because you don't even know what you should be looking for. So to address these spaces, we are working on wrapping a trained neural net when you have the data. How to wrap it as an actor, because actor is all that we have. And the third thing, I mean, if you are not doing generative AI, you better be dead. Okay. So you have to do something about LLMs. So the when you don't even have data and you know nothing, then we are saying, ki, okay, but there is this thing called as an LLM, which is an information store of God knows what. Why not just go to it and see what it has to do? So that's the fourth dabba which we are looking at. We have some ideas, but we haven't validated them even in laboratory. So let me not talk much about it. So if you have this kind of a technological infrastructure, you are now able to address these use cases as follows. So for analysis, it's very easy. Your digital twin is a purposive replica of the system. So you can use it just like you would have used the system. So give the right set of inputs to the digital twin, see what its output is, and if that output is not to your is not expected, tweak the levers, give it to the digital twin and see how. Fairly straightforward. For control is a more interesting problem. Now you need to know what kind of interventions in the first case, what kind of interventions to be introduced is being decided by the human expert. In the second case, we are training a controller who will introduce the right interventions at the right place. So now the digital twin acts as a trainer for a reinforcement learning agent to learn the right policy so that you will know which interventions need to be introduced when. Third is you can use digital twin as a early warning detection system. So think of this scenario. The same input which is going to the system is also being passed to the digital twin. As long as the output of digital twin and the system is in the ballpark same, you know that things are well. But if the output of a digital twin seems to be deviating, then you may say that okay, maybe things could be going wrong. And in digital twin, through simulation, you can compact time. Now you can go 3 months, 6 months, 1 year ahead of the ahead in future to see if things are really going to become undesirable if no corrective action is taken. And if it does seem like that, then corrective action needs to be taken, which through reinforcement learning agent you already have a controller and you will then introduce that action into the system. But this is again of what you know, what you have known so far. For you to expand your domain of knowledge, we introduce a learner component which learns from the external world and it also learns from how the system has behaved so far. So, with these two as input, we update the digital twin. Updated digital twin is then used to train a new reinforcement learning agent, which gives me an updated policy, and that updated policy will do a far better job of control. That's the so long and short of this use case. Okay, this is a marketing slide, so let me quickly go over it. So now let me spend some time. No, no, no. So let me spend some time here. Forget about the right hand part. Okay, that was meant for our management. So the left hand part is saying that we have applied our technology for four spaces. Business space, wherein we have solved some problems in telco, banking, and financial services space, as well as with airlines. Uh, in the cyber physical space, we have solved problems in logistic industry, retail, refineries. And in societal space, this was most heartening. Uh, we created a digital twin of our Pune city to help predict and control evolution of COVID-19 pandemic. So Pune Municipal Commissioner used to take our inputs to decide how should they go doing it. He was definitely talking to so many other people also, but we were also providing our 2 cents. Plus, whatever we did for COVID pandemic, we could repurpose it for the problem of the organization wherein we wanted people to move from work from home to work from office. And it's a multivariate optimization problem. Customer deliverables should not get impacted, and the people should not be exposed to the risk of COVID infection. So, how to do it? Plus, India being such a heterogeneous country, the way COVID used to evolve in different parts of the nation also was different. So to do that was an interesting problem. And right now we are talking to uh, these governmental agencies to solve problems like can you do a flood control of the Krishna River basin near Sangli? Or can you help us come up with a strategic water action plan for Pune Municipal Corporation, etc., etc. So now let me give you a flavor of the kind of applications this technology has been used to. So let me first take the COVID-19 pandemic because everyone in this room is not only familiar with COVID, I think we are all experts now at COVID. We know how things work, right? So here we have to be cognizant of these four parameters or the four dimensions. First is the healthcare dimension, that means our hospital system. So our hospital system is not equipped to cater to the health needs of our entire population. So it became very critical to know how many new admissions are likely to happen in a week. What would be the rate at which these admissions will happen? And how many of these patients who are likely who will be getting admitted will need critical care, maybe in the form of oxygen bed or ventilator, etc. So these were the important questions from the healthcare perspective. From the economy perspective, the questions were uh, what to keep open, how long should the shops stay open for all 7 days, or should the shops stay open on alternate days? Can they stay open for 8 days, 10 days, 8 hours, 10 hours, etc. Not many questions, and we discovered that this shopping lobby is a very powerful lobby, and many in the uh, governance sector they want to be seen as not being uh, responsive to their needs. So they needed a justification of why certain things are good for you and why they are not. That's where these kind of what if scenarios, etc., help. The third dimension is that of infrastructure. Now we don't really have as many hospitals as as we would like. Plus, the large chunk of our population belongs to economic strata where they really can't afford strict isolation at home because the homes are small, too many family members. So we had these isolation centers which came up just to cater to this eventuality. So over there also, their questions were, what should be the size of these isolation centers I need for Pune city? Uh, um, how many? Where? And how many patients will each of these isolation centers need to admit at any given point in time? When it comes to mutant, the questions were infectivity. Is the infectivity of this mutant is high, low? Mortality, is it high, low? Is this mutant likely to escape a vaccine, etc., etc. Now, here we obviously knew nothing of this space of epidemiology, so we blindly relied on the information which used to come in Lancet journal. Whatever they said, we used to take it as God's word and encode it in our model. So now this those four dimensions over there is the problem space. Uh, or these are the goals which you want to achieve. What are the levers at your command? You can keep on vaccinating people, you can keep on testing people, you can introduce lockdowns. You can relax the lockdowns. You can decide what is the occupancy in a particular vaccination center. How long should public spaces be open? Should they be open at 50% occupancies, 100% occupancy, etc., etc., and duration? And there were lots of variables which were inherently uncertain. Mutant characteristics were inherently uncertain. Vaccine characteristics also were uncertain until the vaccine was in use for more than a month or two. Uh, Whether people will follow or whether the people will exhibit COVID appropriate behavior, that was uncertain. And whatever policies that the Pune Municipal Corporation will introduce, whether people will conform to those policies were also an uncertainty. So the model which needed to be created must be capable of addressing these issues. So what we created was a fine-grained digital twin of a Pune city, wherein we essentially created a model to answer these four dimensions. First dimension was about the places, uh, about the people, sorry, demographic information. Who can do what, where, and when. So this is how people are going to go about doing their daily lives. So we encoded that into one particular actor type, that's a person. But we realized that uh, just having one person is not going to suffice because the homemaker, the way she goes about a day of a homemaker is quite different than a day of a factory worker, than a day of a doctor, or a day of a engineer, etc., etc. So we created 47 artifacts covering most of our population. So, and then we populated those 47 artifacts with the Pune demographic information which was available with them. So that took care of the people part. The second part was the places. So over there also we came up with about 17 or 18 different kinds of archetypes to uh, classify places because all that we were interested in was how much time people spend at a particular place and what kind of people spend time at that kind of a place. The third dimension was of virus characteristics, which we just relied on information in the medical journals. And the fourth dimension was the dimension of levers. So now the problem was we populated this digital twin with Pune's local uh, information, and we wanted to know that this digital twin is indeed a fair representation of Pune vis-a-vis COVID. So, how did we know that our digital twin is correct? So, over there, there were very many parameters. We relied only on depth. COVID deaths was the only parameter, and we used to predict COVID deaths over here. And if it matched with whatever PMC is saying, we said that our digital thing is correct because any other parameter was very difficult. Like how many COVID positive is a function of how many people are actually getting tested, and we had no control over that. So death, we hope that nobody is fooling around with deaths. They are reporting it correctly. Who knows? I mean, they might not be, but that was the best we could. So with that, we, so to say, uh, set up our digital twin and then used it for further prediction. And we were able to answer almost all the critical questions for the healthcare, the isolation infrastructure, as well as lockdowns, etc. And we did a reasonably good job. So these are just the pictures. What I would like to highlight to you over here is this thing. The blue line is what actually happened. and the orange line is what we predicted. So the second wave, which almost everyone got it very wrong, we also got it wrong. We got it wrong in the amplitude, but we got it right at when the second wave's onset is going to come. Pretty correctly. But amplitude we missed.
Did you predict it? And how much?
How much are we?
Three months ago. Yeah. But we missed amplitude by 30%. That's huge mistake. Where is the blue line? No.
Again, you don't see the peak of ground.
If you come close, you will see.
Much higher. The peak of
No, the peak was much higher.
Oh,
Peak was here.
oh, I see.
Yeah. We got it wrong. And why we got it wrong was anyway, that's another topic.
No, but is there a brief answer to that? Because that's the most interesting thing in some.
Okay. We had programmed, we had given some um, uh, probabilities to certain kind of people exhibiting certain kind of COVID appropriate behavior and certain kind of conformance to policies. And that was, finger in the wind. And we just didn't know. We thought कि well educated prof नहीं करेगा जाएगा ठीक ठाक नहीं होगा.
So were you able to change the levers to get that behavior after that?
But I mean, it was all.
No, but that makes an interesting paper. The image you have of performing of paper behavior versus what actually happened.
I think correct. So this particular got accepted in a journal, and then we wrote the other paper saying, कि sorry, we were wrong over here, and we were wrong for these reasons.
Okay. Yeah. No, but I mean, interpreting the data backwards, it's like what you can say is, let's say you wanted educated people to behave with probability X. They actually did it with
No, please.
Okay.
Again, as I'm saying, कि I have a certain lens, correct?
हाँ.
Those parameters. Oh, who knows? That means some other totally other parameter. Which may even justify this.
Okay.
I have no clue. So I am saying that within my whatever was available to me, if you could tweak it, I can still justify. But I don't know whether that is the truth.
So roughly, what was the size of this model?
Uh,
Sorry, digital model.
about 100,000 items.
Healthcare.
100,000 items.
Did you model the geometry of the city also?
No.
So they all occupy some common space. Sorry.
No. Okay. Okay. By geometry, you are saying that you
Roads and Kasbapet has much higher density
correct.
compared to Goregaon Park.
Correct. So we introduced. Okay. How do I put it? There is this. See, COVID is all about possibility of people coming into proximal contact, correct? So proximal contact definition is very clear. If you come within 1 meter of each other, it is a proximal contact. We just said that if two people are in Kasbah page, probability of they coming in proximal contact is significantly higher than if they are in human.
No, but that means you did have a geography knowledge.
I mean, ideally speaking, someone would really like to have a spatio-temporal model in place.
Yeah.
We didn't have it. We just force-fitted those ideas into whatever parameters we were controlling or we were modeling.
Essentially, the actors are different characters.
Yeah.
But then the whole, the framework under which you are creating this system, it allows for these geometric constraints to put in. Like can you model Twerk Road and Lakshmi Road, Bajirao Road and put it into the little bit?
Yes, but I'm doing it slightly differently. We are modeling river. So we are modeling Ohio River and we are modeling the stretch of Ganga from Allahabad to Kanpur. Is it Allahabad to Kanpur or Kanpur to Allahabad? I don't know. So I don't know which way the Ganga. Yeah. So that's So over there, we are taking care of geospatial or yeah. But that's not much easier because just one dimension. Whereas over here, it's actually a three-dimensional space.
The whole network.
Yeah, and it's time, so it becomes really very. But somehow, yeah, everything was done. ये तो नया Mac है. This was old Lenovo that I had. It was done on an old Lenovo.
That's it.
So the resource constraint just didn't allow you.
You are able to do 100,000 actors on a laptop.
Yeah.
Very interesting.
Yeah.
There's a question on
Yeah.
that. So how often was the model updated with actual data, and was it just initialized and everything else in one shot in the beginning?
No.
How often?
Well, to be quite honest, whenever we used to see that key, the model is going really off the block as regards predicting of death rates, etc. Then we used to say that was something is wrong. Now we have to fix the model. So it was done on a need basis.
But in an ad hoc way, not a
No.
modern modifications
No,
where you would think, oh, maybe this is wrong and you just do it.
no.
But no. So what was the methodology then
Yeah,
for modern modification?
yeah. Okay. I mean, it was an art. I mean, there is no science to it. Like for
Yeah, no, that's not
yeah, correct. So like we had Pune is 17 wards, right? So we had six prototypical wards. When we did model 17 wards, we classified into six ward types, and we created a model for each of that ward. I mean, the same model was populated for each of that ward, and it was just a sigma of all with appropriate three of this type, five of that type, that kind of a simple algebraic equation. Now, when you used to say, कि, oh, death prediction गड़बड़ हो रहा है, oh, which part type में death prediction गड़बड़, oh, guns fate, nana fate में death prediction गड़बड़ हो रहा है. Okay, guns fate, nana fate are heavy dense, lower economic strata, etc., etc., etc. So probably the parameters which we have given pertaining to certain characteristics of people, those are wrong over there. So just fix them. That's how it was an art. There is no science to it. And yeah, we fiddled till we got reasonable result. But then everyone says that all models are wrong. But some are useful.
But what about number of parameters?
Okay.
Roughly, order magnitude. Tens, hundreds, thousands.
Okay. Each actor had about we had 47 actor types of people. We had 17 actor types for places. We had about 20 odd actor types for vehicles. And each actor had about 8 to 10 attributes. So you can see the parameter space.
Thousands.
Yeah, it's big.
Yeah.
It's big.
Yeah.
And so,
So that means you had some idea about how you can't. If this is a art, and you say something went wrong, now you want to fix it. You can't fiddle around how this what happened. You really need to know what these three parameters have been checked.
okay. See, we are just computer guys, right? We know nothing about this space. We were working with Prayas Health Group of Pune, and they had epidemiologists, they had demographic experts, etc. So they used to say, "Oh, Nana Pet mein ye ho raha hai. Don't have to worry about Viman Nagar area at all. These are the parameters that we should focus on." We just went by whatever they said. We didn't know how to change the model. We knew how to change the model. Right? We just changed. The second thing I would like to talk about is decision making in a telco. I mean, this actually is a generic problem across all services industries. So, any services industry is can be viewed along these three dimensions. You have a dimension of customers, you have a dimension of products, and you have a dimension of customer care. The name of the game is you should uh, onboard the right kind of customers, and the right kind of customers should stay with you for right kind of time. Therefore, you need to have the right kind of products. The customer should be given the right kind of service. Unfortunately, uh, which customers to onboard, what products to develop, what kind of a customer care services to be given. All these three questions are answered, are addressed completely isolated manner. It's the marketing guys who decide customer kaun sa chahiye. So it is the product guys who decide what product should we bring out to the picture. And it is these customer care people who decide ki, this is the best I can do with the customer. So as a result, it becomes very difficult to ensure the overall objectives of a telco are met. And as you know, telco is one of the worst service industries. They will not like it, but they have the lowest customer experience amongst all services.
So by telco, you mean the shops where you go to repair your car, the service industry, or how is telco a
No,
service?
telecom. By telco, I mean telecom.
Telco.
So,
I thought you meant the Tata
No,
Motors.
it's telecom.
Nowadays it's called Tata Motors.
Yeah, okay. It's telecom. So they have a very high.
Like lowest customer. I know that.
Yeah, that's quite correct. That's quite correct.
Broadcast and recorded to the you know.
I mean, yeah, correct. That's a facts. So, what we did was we constructed a digital twin of the customers, the products, and the customer care processes. Of over here, this work was done for a big telecom major in US, and this model was really huge, uh, close to 1 million actors, and it was run on a high-end computer, wherein we were able to do amongst the routine things like predict what would be the average monthly revenue, etc. They had one very peculiar use case. On the advent, as they saw COVID is well upon us, they realized that everybody is now going to work from home. So they realized that we should give them an unlimited data plan. So that everybody is going to be working from home. They will definitely want to have an unlimited data plan. But they did typical segment-based product testing, A/B testing, etc., etc., and they came up with certain answers to what all features need to be there and what should be the price point, who are the people whom we should be targeting, and how should we go about launching this particular product. And they realized that this is not meeting their expectations on ground reality. So, I mean, they're actually, it was posed to us as a challenge. Okay, you guys are claiming tall things. Please solve this problem for us and see if you can come up with a better solution. So, through this digital twin, we came up with better answers for this, which, when implemented, did uh, far better than what they were witnessing, that they had witnessed on ground. So there is a testimony that these this kind of technique indeed works on ground. I'm actually overshooting.
Yeah, little bit.
Yeah. So I'll quickly stop. Right? Stop. So okay. See, now this is going to be unfortunately very software heavy, so I won't spend much time. Okay. But what we realized were three big problems. I mean, we have been doing this for 4 years now. And the big problems that we came up it used to take a lot of time to construct and use digital twins. Because constructing a digital twin is analogous to writing a program in that special Java. And manually writing program was very hard. So enhanced automation was a key. And we also realized that these are business problems. So we should empower business users to do this kind of work rather than they telling some techie guy implementing those requirements. And most of these people had lot of knowledge available with them, but they just didn't know how to operationalize that knowledge. So this forget it. This is yeah. So we are now using large language model as a model construction aid. The intuition is as follows. Uh, if you have a modeling expert, he will be able to do a good job of creating a model, but he doesn't know any of those modeling techniques. Problem number one. Problem number two, there aren't enough modeling experts. Most of people whom you have are novices. They are comfortable with a domain, but they are not expert in the domain. So they don't have all the knowledge that needs to get encoded into the model. So since answers to everything these days is LLM, what we say is, okay, would it not be nice if someone who is not an expert goes to LLM with focused queries and gets a response from the LLM to that focused query? But that response is going to be in text. But instead of viewing it as a text, would it not be nice if I am able to capture from that text the relevant model? So think of it that no. So I go to the LLM with a question which is derived from a meta model. Meta model to model relationship is programming language and a program.
So every student is already doing this for the assignments. So by the time this is everybody will be used to it.
Oh, very good. So, this way, we believe we will be able to construct models faster, better, and cheaper. And now that you have a model of a digital twin in place, how to generate an implementation of a digital twin in whichever programming language of choice is a done deal. So that can be done very easily. This is what we have done. Second problem was operationalizing the knowledge. Most of these telco companies, retail companies, they have lots of information with them, which they would like to get encapsulated into the digital twin. And this information is of a quote unquote sensitive nature. So they are not going to let TCS guys do it. They want to do it themselves. But they don't know so much of this technological jig bag. So would it not be nice if we give them with technological infrastructure wherein so, which supports this think, execute, and observe kind of a cycle. So the whomsoever is trying to operationalize, he thinks, okay, what is the question that I should go to LLM, and what is the local context that I should provide it to the LLM, and when I get an answer from an LLM, I should check whether I have got all the relevant information back. If I did, if there are some blanks, white spaces, then I should know. I should now go to the LLM next with this kind of a question. So that's if you have some sort of a roadmap in terms of big questions to be answered, and for each question, if you support, if you can operationalize this think, execute, and observe loop, then you will be able to operationalize all your knowledge in a more uh, directed manner. This is something which we are doing. And eventually, the idea is to have an integrated platform where this knowledge infrastructure, the generative AI infrastructure, and the MDE infrastructure all exist together with a conversational agent as the only interface. With that, let me come to the last slide. We believe future is all about complex dynamic system of systems. Decision making is a very critical problem. Nobody has a good answer to it. We think we are on the right track, but a lot needs to be done. And for those interested, we are open to internship, master's thesis. We have lots of problems. Unfortunately, we don't have solutions. Bright people like you will be able to help us come up with the solutions. Yeah. And if you don't have anything better to do in life, then you may go and read this book called The AI Enabled Enterprise, which Springer is thinking about. Where some of these ideas are there. So with that, thanks for patient hearing.
Is the The COVID code available,
No,
you're not willing to share it. Curious one.
TCS IP, sir.
COVID?
It's not COVID, no. The code is in our language. And you will say, okay, give me the language infrastructure also.
This public, that's what.
No, there is a eclectic avatar of that language which is there in public domain.
Oh, okay, I thought.
But there is a more production heavy avatar of that language which
Okay.
TCS uses to make money there.
Okay.
Yeah, that's the only way you can work with people like you in academia. We have to come up with a language which is for everyone to access, they can play with it, and we keep that language intentionally non-performant. That's life.
Questions?
You said that the actors are asynchronous.
Actor model of computation is purely asynchronous. Yeah.
But there's a global clock, right? At least.
Yeah,
you have
yes,
implemented.
yes, there is a global.
Okay. And actions have some specified
Yes.
delay.
Yeah, correct. Well, philosophically, no, but if you have to implement it, you have to use that caveat. Okay. Otherwise, it becomes impossible to simulate.
I also have a question on your COVID model.
Yeah.
So there was stochasticity involved, right?
Yeah.
So then it's kind of a Monte Carlo simulation.
Yes.
And so do you do 1 million runs of that? So do you do
That's
one run of
that's another art. You need to know how many runs to do. Because see, essentially the name of the game is I must cover all the paths in my model. So as to be sure that the simulation run is not excessively biased in one way or the other. So I have to give the right kind of data, but because it is stochastic, just giving the right kind of data is not going to guarantee that everything is going to be covered. All the probability distributions are going to be covered. So how many? 100, 200? Yeah, we have to do that. I can't say with confidence. I mean, we have to look at the output. We used to, in our technological infrastructure, we also create a trace. And we used to then mine the trace. I mean, is everything covered? Is everything not covered? Because who is going to look at those KPI graphs? No, I mean, it's impossible. So we developed some technological machinery to help us answer those kinds of questions, whether we have executed enough runs or not.
So when you say there's a like second wave that is being predicted, but you have hundreds of runs and different things happen in each of those hundreds of runs, then where does the graph come?
Huh.
Is it the average of the 100 runs or is it something more interesting?
Mean or medium?
You can't have a median of a graph. It's not a number. And how do you take a median of 19 to our function?
No. I mean, the way it works, whenever there is a change in the model, and I have to now run it for particular simulation, we used to do this Monte Carlo kind of a thing, 100, 200 runs to get convinced that, okay, this seems okay. So, and then give take an average of what is coming out and project it out as the likely out.
So the graph is averaged by time.
Graph is average by time.
Questions from students?
Yeah.
Okay, so each actually system, we have each different actors and each functions.
Yes.
That means you'll have to build up your own, let us say,
Yes.
castle kind of thing.
Yes.
Every time.
Yeah.
Sure.
So it is,
Yeah,
think of it as
yeah.
you have so many Java classes here. Just like that.
Yeah, and there is at least one company I know of which apparently offers this stuff on the cloud. I don't recall the name. but they created one of those Y Combinator. People have a startup doing.
No, there are many companies which offer uh, agent-based models on cloud.
Yeah.
The essential difference between agent-based model and an actor-based model is agent has a very simplistic behavior, but the number of agents are really huge, tens of millions. Whereas in actors have complex behavior, and they are not that huge. But even we had about close to a million actors in one use case.
More questions? Okay, if not, let me request Professor Vanpurkar to present this. You mentioned all models are called, so we have a little moment of saying the same thing.
Okay, thank you, thank you.
By the way, this choice of images comes from Ajay Nanda, your colleague.
Okay. Thank you. Yes.
Okay,
Yeah.
thank you.
Thank you very much.
All models are also that code. Yeah. Clear? So, Ramila तीन साल बाद ना हो तो about that's the slide box the kind in initial thing
GEP.
the George box
Done.
the was the
Second.
don't need that about it.
Yeah, very nice.
Yeah, buddy. Okay, boss.
Slide 7 through the